the DOE start in the use of DOE start in 1930s, 1930s with the guy named Ronald Fisher. Okay, how this start is that this Ronald Fisher, he observed that the way there are many flaws in the ways experiment is conducted. Okay, this Ronald Fisher, he worked in agricultural, mean that he worked with the growing something. So agricultural. So we can say the first period for DOE is agricultural era lah, the first era. We call it agricultural era because this Fisher, they perform DOE based on this this field. Okay, so Fisher come with the three main he developed the three basic principle of conducting the experiment, which is first is the replication. Second is randomization, and then the third is blocking. Okay, and also Fisher also introduced the factorial design, the one that we learned before, factorial design. And also he mean that he used the statistical analysis, especially the ANOVA. Okay, so this is how the DOE start. So let me make it a little bit smaller, so it's a little bit big. So this is how DOE start by Fisher. So I will later go a little bit detail on these three things: replication, randomization, and blocking. Even though now we think that this is normal, but back then many experimentation done without this principle lah. They just do haywire, and then because of that they still can get result, but maybe not as much as they should be get if they use proper experimental method. Then come what we call in 1950s. Now in 1950s, there are another guy named there are two guys whatever, Bock and Wilson. Okay, so this is basically they start to introduce what we call the RSM. Okay, you heard about the RSM. So this part they call it industrial age. Industrial. So let me draw like apa ni? Like gear. So this is industrial era. Okay, so this Bock and Wilson, they found that what we call the industrial experiment is different than agricultural, because when you do any experiment with agricultural, you need to wait a long time, like you grow a crop, so you need to wait a long time. This Bock and Wilson realized that because industry, they what we call, they are fundamentally different than agriculturals because of these two reasons. First, the first reason why they are different, because of they are immediacy, meaning that respond when you do something in the factory, the response that you can be observed immediately. Okay, rather than when you grow a crop, it takes like a long time, a month to what we call, to observe the response. So when you work in an industry, I mean the normal engineering whatever, the response typically you can observe immediately. So that's one thing, immediacy. And the second thing that is differ between industry and agricultural is the sequentially, meaning that the experimental can quickly learn a crucial information from a small group of friends for the next experiment, meaning that they don't do like the grand experiment. They chop their experiment into chunk, and then they start small, and then they, because of the immediacy, they get the result early on, and then they use that result to go further, a little bit bigger and bigger. That's why when you see the DOE, you can see they start from what? From, if you see this overall flow for DOE, it start with this, the screening. So this like a one chunk, and then go characterization, go optimization, go confirmation. Even though for us now, we see this for granted, mean that, oh, this is normal, but back then it's not like this. They just do the experiment, find something, and then they just do try error, and so on. Okay, so that's for the second era lah, we call it second era of DOE. And then come the 70s, okay, 1970s, come the guy named Taguchi. Okay, so this guy, he basically what we call, he tried to sort of like, he introduced what we call robust design. So we call it, he introduced what we call robust design. Robust design is basically he tried to conduct the experiment with very less runs. So he developed what we call highly fractionated factorial design. So think like a Taguchi, for example, if you see in the design aspect software, let me open the design aspect software. Okay, wait, let me open first, because I want to show you where is the Taguchi. Okay, wait. Okay, so this is design aspect software. We will use this for the practice later on. But if you look here under factorial here, if you open, you have in the miscellaneous, you have Taguchi, and you also have Plackett-Berman. This type of design is highly fractionated. So the design is not like cube. Before, when we go for factorial here, the design is like a cube, right? But under the Taguchi and Plackett-Berman, the design is a little bit different. It's really less number of run is needed for this thing. So this thing bring a lot of controversy, bring a lot of discussion and controversy. So this, because of this, they have a lot of discussion and controversy. Many said that even though the what we call Taguchi design is well founded, meaning that the idea is there, but then they have this problem with the implementation in terms of method and analysis. We learned before, when we use a full factorial, we get all the interaction. If we use the fractional factorial, we got maybe something. But if we use very fractionated factorial, then maybe you cannot detect some effect, some main effect, and this thing. So that's why people say, even though the concept is well founded, but then the implementation, the method analysis especially, is very controversial lah. But the positive outcome of this, so they also have positive outcome. Outcome is that they generate a lot of interest lah, and DOE start to be widely used. So DOE start widely used because people try to argue here, argue there. So DOE widely used at this time. And now come at the fourth era, which is current era lah, now lah, present. So now we have this renewed interest. Okay, previously only the industry, the practitioner, interested with DOE. If you heard about the thing like Six Sigma whatsoever, so that's quality control stuff. So that's they work with DOE so much lah. But for the academician, for the what we call researcher in the university and so on, this quite new for them. So the present era is basically they symbolize the renewed interest of statistical design. Okay, we call it renewed interest, especially in statistical design. Because previously, if you are in the university, in the lab, in whatever, the research academy, you don't really care about statistics. You just do and get the result, fine. Go effect, fine. But here, there are renewed interest of statistical design. So you need to use analysis also for both practitioner and also researcher. Okay, so now both of these things, both industry and non-industry, they start to widely use this thing. Okay, so that is conclude the fourth era, the first era, the second era, third era, and fourth era. So now you know the where the DOE start. But I want to focus these three things: replication, randomization, and blocking, because this is the principle for DOE. We start with replication first. Let's go down. Let's go down. Let's go down. So here, okay, replication. What is replication? Okay, and why? So the idea is this: the more data, you get precise. You have this more precise conclusion lah. More precise conclusion. So this is because of the power of averaging lah. Due to the power of, we call it power of averaging lah. You have more data, you can average more ni lah. So replication, they improve the chance. This improve chance to what we call to separate signal and the noise. Okay, we remember before we have this thing, this what we call this system, and then you have the response, and then you have the factor, and then apart from this you also have noise. Okay, so you have factor and also you have noise. So when you do replication, you can separate this factor and noise better, and that's why you do the power calculation and so on that we learned before. And replication is not the same as repeated. Replication, let me go down. When we say about replication is not the same as what we call repeated measurement. It's not the same of then compared to repeated measurement. Okay, so for example, let's say you make a screw. Let's say you are here and then you make a screw. Okay, you make a screw. Okay, so you know that the dimension for the screw is critical. The dimension is critical. Okay, so you want to make sure your screw always, the screw that you ever produce from your factory, have the same dimension. So replicate, what does it mean by replicate is that so let me put here, replicate meaning that you use a different screw to measure lah. You have apa color ni? So you have this thing, you have this, and then you have another screw, meaning that you measure different screw. If you do what we call repeated measurement, is this repeated measurement. Let's say repeated is like if you have a screw like this, one screw, and then you measure many times, meaning that you measure this. Okay, you use a ruler or whatever caliper to measure this, and then this is first measurement, and then you measure the same screw, measure the second measurement, and then you measure again because you want to find the average. You measure again the third measurement. So this is repeated. It doesn't count. Okay, you want to replicate, you want to measure different screw, then you can use a statistical analysis. Maybe you can say, okay, this is who do this thing. Okay, this might not be happen, but what common is this. Let's say what common in experiment is this. Let's say you have, let's say you want to make screw, you want to make a screw, and then in order to make this screw, you have the mold. You have mold, and then let's say you have mold, meaning that let's say this mold can do 3 screw lah, meaning that you pour the hot metal inside this thing, and then it becomes screw lah. So one mold accommodate 3 screw. Okay, so let me make it smaller. So one mold, so basically one mold accommodate 3 screw. Okay, so you can do this molding again and again and again. What people do normally is that they make a screw, so meaning that now they have 3 screw. They have 3 screw. Right there. They have 1 and 2 and 3 screw. But these 3 screw come from the same batch, and then they measure these 3 different measurement. They have measurement 1, measurement 2, measurement 3. Even though the screw is the different, but then it come from the same mold. So this doesn't count as replicate. Many experimentation happen like this. they make like what we call a specimen from the mole. Maybe from one mole you get like 5 specimen, and then they use that 5 to get all the data. Okay, so the correct way, if you are really you want to use this replication way, is that you are not using this. You are basically you are taking mole, Control C, and then Control V. Let me make it smaller. Okay, Control V. Let me make it smaller, and then you Control V, smaller, and then let me take this, put here, take this, put here, take this, and put here. Replication meaning that you take you measure from this different different block of mole, the same mole lah. Let's say this mole is the same mole. So let's say this is count as one measurement. It doesn't matter whether you count one screw or all 3 screw. It doesn't matter. But at least for you to do replication, it need to be totally different. Because if you do from the one batch of the mole, then if that process have some problem, then all the screw have some problem. So if you take the measurement for each of the screw at that mole, then it's not really tell you much. So that's why you need to do, like you finish one mole, you measure, that's count as one replicate. And then you take you take away the screw, and then you do another mole, you do another screw. So that is second batch. So then now that's considered as replicate lah. Replicate. So normally this is the this often happen lah in but that is not correct way lah. Okay. Because if something happen to this mole during that process one, let's say you do this. Let's say you do this at morning, and then you do this batch at the night, and then you do this at afternoon. When you do different batch, then you can see the variation between the between the production. But if you do only one like this, then you cannot see the variation. Whatever you get is not randomized enough. They are not replicate, they just repeated measurement. Okay, so I think that the thing about this. So example for this, not example, but I can show you. Previously we learned about the factorial. So let's see this thing. Let's say you have what we call you want to increase the yield of something. So let me bring this thing. Okay, let me make it bigger a little bit. Okay, so let's say this is the factor that you have. Okay, let's say you have two things. You have A and you have B. Okay, so you want to mix these two together. So basically the experiment is that you want have A go into, and you have B, make the different color, B go into, and then you get something A and B, and then from this mixture you get maybe some improved yield or whatever. You get some response lah. You get some response. So now to replicate this is basically means like this. When you put in the factorial design, you get something like this. Let me put here lah. It's difficult lah. Wait. Okay. Because let me put this thing here. Okay. So okay. So to replicate this design, what does it mean? To replicate this design is to do this. Where is the thing? Okay. Okay. So you do something like this. Okay. Something like this lah. Okay. Let me put here top a little bit. Okay, it's okay. So now when you put when you do this is two factor. If you look here, there are two factor. If you do 2 factorial, 2 by 2 at 2 level, low and high, because you see here they are low. Let's say I put here, they are low here. This is low, the negative is low, and then the positive is high. So when you put in the design, they will try to randomize everything. So that's why you see first run is low, second run is high-low, and so on. They try to randomize the whole thing. So in order to do, so when you put this thing, because you have 2 factors, so the total you have what? You have 4 experiment. So that's why you have 4 here. So in order to do replicate, you need to what we call you need to what we call, you do yourself. I mean, you don't put replicate in the design. I mean that some design have the replication inside that, like response surface RSM, they have replication inherent in the design, meaning that if you see the what we call the layout for response surface later on, if you do the thing, if you put the value, you will see some of the run will be the same. If you look here, they are, let's say this run number 1, run number 2, run number 3, run number 4. All run is different. Okay, all run is different. So if you do factorial, then there are no replication there. There are no replications. You need to introduce yourself lah. You need to introduce yourself. How you can do it? By do it 3 times and then find the average. And how you do this replication is by the one that we show before lah, where this thing lah. You need to understand how to do replication, not to be confused with what we call the measurement lah, with the repeated measurement. Next, after we learn about this, so now we have done with the replication. So we done with this thing, replication. So now let's look at second principle of good design or experimental design. Second is randomization. What is randomization? Let me go down. Randomization. Okay, let me put here randomization. Okay, randomization. Okay, randomization, the purpose of you do randomization is to make your assumption valid. To make your assumption valid. That's the purpose of you do the what we call randomization. What it actually mean is that your runs, I mean that when you do the experiment and also your material should be randomized lah. Should be randomized order lah. You perform the run in random order. Okay, normally when you put in the design software, they already randomize it for you lah. By randomization, we also average out the noise that may present in the system lah. For example, if you deal with the person, let's say if you deal with the person, then this person sometimes can be highly motivated. Sometimes what we call this person, the same person can be very tired, and so on. So you need to randomize the order in order. And also if you deal with the machine, then the machine you need to consider sometime what we call, if you have a machine here, let's say you have a machine, whatever machine here. So this machine, let's say you want to test something using this machine. So this machine can warm up, can be either just warm up, or this machine can be either already fully start lah, fully warm up. So when you do randomization, you sort of like average out this problem. Okay, so for example, it will randomize all this thing lah. I give you the example. Let's say you want to do this thing. You want to test the hardness of specimen. Let's say you have this sword. You want to test the hardness. You want to test the hardness of this sword. So one factor that can affect this hardness is basically quenching. Basically you put this sword in some liquid lah. So that's what does it mean by quenching. Quenching is basically you put this metal or whatever in the water. After you produce, it's hot, and then straight away you put in the water or in the oil. So the quenching here can be done either in water or in oil. Okay, let's say this experiment. So if all the experiment, let's say if all the experiment for the water, you use the thicker sword. For example, let's say you want to test the hardness, and the hardness here, let's say the what we call the function of hardness here is basically thickness, meaning that the thicker it's not the thickness. I mean that it's not just the hardness. Okay, so let's say the sword here, if you look here, if I put here, and then if you look from the side, you can see like the thickness lah, the thickness of the sword, the thickness of the sword. So if let's say you do all the tests, let's say you have the sword that you use to quench in water is a little bit thicker. Let's say you use the sample a little bit thicker for this, a little bit thicker, and this is normal what we call normal thickness. So then you will not get you will get the result, but the result can be misleading because you sort of like bias. You always put the thicker dimension sword into the water, and only the normal and thin what we call thin sword on the oil, in the oil. So in order to randomize, you need to random the material itself and also the order. For example, you put what we call the this thicker sword can also go to oil and water to randomize everything. Okay. So the solution is that lah, to randomly. So the solution for this is to what we call to randomly assign the specimen or the sword here, the specimen to quenching media or liquid lah, media. So that's what does it mean by randomization. But there are times that when you cannot randomize, when there are times that you found that what we call, you want to perform randomization, but it can be totally inefficient or even impractical to do randomization. For example, if you have something called HTC is basically the hard to change factor. Okay, give you the example. If you found something that is hard to change, let's say, give you an example. Let's say in the laboratory, you want to grow the bacteria. Okay, you want to grow the bacteria. Let's say in the bacteria, but you only have one incubator. Let's say you have only one incubator. So this is your bacteria inside this. Your bacteria. So incubator is basically to regulate the temperature. So that if you say 37, so it's 37 lah. So that's bacteria inside this. You only have one incubator, and then for this experiment to finish, it takes maybe like 2 months or 3 months. Let's say it takes 3 months for one experiment to finish. So this normally happen when you deal with fungus and so on. You have only one incubator, and when you have one incubator, you can only set the temperature at one times at the moment. Meaning that if you set 37, it's always 37 Celsius until you change it. So let's say this, you have, for example, let's say the temperature, let's say here. So let's say the temperature that you need to change is, that you need to test is maybe 30, 35 and 37. Let's say you need to test 3 temperature, but you have only one incubator, and to finish one experiment it takes like 3 months. So it's what we call, and that's fine, but then you need to understand when you do the when the design give you the need. Let's say you have the design, they give you something like this. Okay, they give you something like this, plus plus minus plus 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 minus plus, meaning that if let's say like this, let's say you have like, let's say total you have 16 run. You have 1 2 3 4 5 until 16 run, and this 16 run, the software will randomize the run, meaning that if let's say you have temperature here, so let's say this temperature, and then let's say this something else, maybe pH, you want to test the pH. Let's say another thing, you have like three factor that you want to test. Another thing maybe humidity. Let me put myself up. Humidity. So you have 3 factor. Let's say you have until 16 run. So when you put the factor inside the software, assuming that you use 2 level mean that temperature can be, let's say you just use 30 or 37. So you have 2 level. and then pH you want to test between 6 to 8, and then humidity maybe between 20 to 80. So the design, when you put in the what we call in the software, it will give you, let's say this is minus, this is plus, this is the low is minus. Let's say we put low level is minus, the high level is plus. They will just randomly assign plus, plus, minus, plus, plus, minus, plus, minus, plus, plus. Yeah, they not randomly assign. I mean that they have the design, but the run itself will be random. So if you look here, if you look from here, look at the temperature part here. If you look at the temperature part, you see a negative here, low level, low level, low level. By right, you should do this run number 1. You finish run number 1 first, and then you do run number 2. You cannot go run number 2 before you finish run number 1. But if we said that before, for temperature is too inconvenience for you, because to complete one run you need 3 months. So what you can do is that you sort of like take these 3 and then what we call combine them together, and then you run this in one thing, because you put all these 3 inside this thing. So that's what we call you don't do randomization, but here what we call is you are doing what we call blocking or split plot. Split plot. This is what we call blocking or split plot lah. The term is split plot or blocking lah, or another term that people use to do this thing is blocking lah. So if you look at the design here, if you see design, you have this what we call the split plot design. You also have the response surface, also you have a split plot design for that. Okay. So the idea of the split plot, why they call it split plot, is because they come with from the agriculture. It's happened. This thing start from this. When you we talk about the what you call the history, you can see here. First is agriculture era. So this Ronald Fisher, they introduced this split plot method lah. So the idea for the split plot is this. Let me bring this thing. You have this thing. You have, for example, let's say you grow the what we call you have the whole plot. You have the whole plot like this, and then you want to test the herbicide. You want to test the herbicide for this corn, potato, and wheat. Okay. Let's say you use herbicide A. Let's say you want to use herbicide A. You sembuh pula. You try to spray the herbicide here. Spray the herbicide here, and then you want to spray the B. So B you want to spray here. Okay. The problem with the herbicide is that it's a spray. It's like aerosol. So it's well the wind. If you have the wind, you will get drift. Okay. Because these two things is near each other. So maybe this herbicide A will go to this thing. So it will sort of like what we call cause the problem with the result later on, because now you have the mixture of herbicide. You want to test each herbicide, okay, but because of the drift from the wind, then you cannot. So what they do is that they split the thing into plot. They split like this. Okay. So so let me pick this thing. I put this here, and then I bring this. So if you look at this second figure here, you can see now they divide into 3 different plot. And then they sort of like separate this plot far enough in such a way that if they they group thing lah, they nested the thing. So this here just herbicide A. They do herbicide A. So regardless, even though they are wind, so the wind will sort of like drift the herbicide, go to here. It still doesn't matter because it's still herbicide A. So this range here is far enough to avoid this one herbicide goes to another plot. So this what they call the split plot lah. So they split the thing, they random also the crop in the subplot, but the key idea is that now they can do herbicide B here, so they don't care whether the wind drift their spray their herbicide here or not. because they do the split plot. Okay, so that's the idea of the split plot lah. Another concept, another way how you to do split plot is this. Is let's say you want to do this experiment. Let's say I put here. Okay, let's say this thing is the experiment, the first one. Okay, I put A, I put B. So the experiment is this: you grow a paddy, and then you have two what we call two not two variety, meaning that the E is basically early soon, meaning that you sort of like you sow that paddy early of the year, meaning that from in January lah, maybe in January what that, and then you have another one late soon, maybe you what we call you put the paddy on their place on July like that. Okay, so if you want to do it randomly, that's you need to do like A here, you need to do, you start with early first and then long. Let me put it. So you do this early first, you finish this first, and then after you finish, you continue with this, and then you continue with this. The problem now, for the paddy to grow, it takes time. So if you start this on January, and then you finish, let's say you finish, and then you need to start this on July. Okay, and then you need to start this on July, and then you need to wait next year January in order to start this thing lah. Because if you do it together, then it's not a random order lah. You do it together. So that's why the split plot, the split plot is basically you try to gather them together. So this thing, to gather them together. So basically you test 1, 2, 3, 4, 5, 6. Maybe the numbers here, maybe the variety of the paddy lah. Numbers. So numbers signify variety. So you have 6 types of paddy lah. You not test. You want to test. So you test in one block and the second test in another block. So you can finish everything in 1 year. Rather than you do it like this, then you can block the thing and you can finish it easily lah. But split plot make things easy, but as usual, anything that's come easy, there will be a catch. Okay, there will be a catch. Okay, so you cannot see in this case, in this case you cannot sort of like check the difference between group lah. Okay, the difference between group you cannot really check. Okay. So in other words, when you do this blocking or split plot, you lost this power of some what we call to assessing the factor between early and late. For example, now if you do like this, you can assess the power between early, late, because you are different. But here you only have one type of what we call testing between early one group and late one group. So they are not enough for that. So you lose the power of this significant of ni lah or in the analysis. So that's the catch lah. So you will see when you do split plot, the effect will be on the power, the what we call the significant power, because we learned before that in order to calculate the power, you need to do signal to noise ratio, and then you get the power. But when you do this split plot, you will find that your power will be greatly reduced lah. But sometimes this is the only way lah when you want to deal with the hard to change factor HTC. So sometimes it's impractical to do randomize after all. So this is where the split plot or blocking method come into place lah.